Hey there, students. I hope everybody's doing well and staying safe. I thought I'd pop my face in here and say hello. Um, so let me give you a bit of an update on where we're going with grade 11 physics. Obviously, we need to cut some things from the course, and we're not going to be able to cover any of the units in quite as much detail as we would if we were in school. So we need to move on from the forces unit pretty soon. The last thing we're going to do is a problem set. So I got you to learn the friction topic on your own by taking notes from the textbook. And we're going to take that in combination with the last few topics, including applying Newton's laws to kinematics problems. And you're going to solve a problem set of 10 questions, which I'm going to mark. Now, everybody has a different set of 10 questions. It's sort of randomized. And some people are going to have harder questions than others. And the reason for that is some of you are at different stages than others. One of the nice things about remote learning is that it sort of allows us to take more of a custom tailored approach. Now, before you yell at me, it's not going to affect your mark. If I'm giving you harder problems, it's not going to bring your mark down. Don't worry, I'm going to make sort of adjustments around how difficult the problems are. But the reason I'm doing it is it's going to be more effective for everybody that way. Like if you understand the basics really well, you shouldn't be doing basic level problems. You should be challenging it. You should be getting challenged a little bit more. And if you are still learning the basics, then you should be doing the basics in order to learn them better. So that's the basic idea. Now I'm going to give you your 10 problems, and you're going to have about a week to finish the problem set. I really strongly encourage you to start working early. So the moment you get the 10 questions, give them a shot. You might not be able to solve them all right from the start. And so what I'm going to do is I'm going to be releasing example questions throughout the week. So basically one a day. And so I'm going to be solving problems on a video and then post it online. And there might be something in the video that helps you solve the problems in your problem set. Maybe they're very similar questions. Maybe there's just one idea that will help you. But it's always more effective for learning if you try it yourself first. Even if you don't solve it, as long as you're thinking about it and like researching it a little bit, even if you don't solve it, it's always going to stick more if you try it yourself first. So please, I urge you strongly to try these problems yourself first if you really want to be learning this content as effectively as possible. Okay, so without further ado, let's get to the first problem. Friction! Okay, so here's the first problem. We have a 3 kilogram block of wood sitting on a horizontal wooden floor. So let me just draw that out. So here's a floor, here's a block of wood. It is 3.0 kilograms. The largest horizontal force that can be applied to the block before it will start moving is 14.7 newtons. Once the block starts moving, it only takes 8.8 newtons to keep it moving at a constant velocity. Now this gets into the idea of static friction versus kinetic friction. So it's harder to start moving something than it is to keep it moving once it's already moving. And so basically the coefficient of static friction is always higher than the coefficient of kinetic friction. And that's what those two force values are about. Okay, so we have to calculate, part A is to calculate the coefficient of static friction for the block and the floor. So the formula, which you should have discovered in your research, is mu equals, wow, I'm forgetting this. It's force of, I need to do some rearranging myself just to get this right. Force of friction equals mu times the normal force. So therefore mu equals the force of friction divided by the normal force. Okay, so let's see. In this case, the normal force is equal to the gravitational force because we have, I'm just going to draw a free body diagram. So we have the normal force going up, the gravitational force going down. We might have some applied force. Yeah, probably somebody's pushing it. And then we have a force of friction going back the other way. Okay, so the normal force is equal to the gravitational force. So the normal force equals mass times g, which is 3 times 9.8. 29.4 newtons. Okay, so remember we're trying to find the coefficient of static friction. And so that the coefficient of static friction is about getting the block moving in the first place. And so in the question, it says it takes 14.7 newtons to get the block moving. Therefore, that is the maximum amount, that's the maximum frictional force that can possibly be acting on this block. So therefore, in this case, we would say the frictional force is 14.7 newtons because we're assuming the frictional force is as large as it possibly can be. And okay, so that's it. We just need to plug the numbers into that formula now. So mu s equals 14.7 over 29.4, which is, 14.7 divided by 29.4 is 0.5, exactly. Wow, I should have done that in my head, I think. Okay, part B. I'm going to try to squeeze this all into one page. I've probably taken up too much space already. Part B, determine the force of friction acting on the block if a horizontal force of 6.8 newtons acts on the block. Okay, well, we already know that the force of friction can be much larger than 6.8 newtons. So therefore, if you push on the block with 6.8 newtons, friction's going to push back and not let you move the block. So the block's not going to move at all. But it's not going to have this much friction. If it had that much friction, it would start to accelerate backwards. But that doesn't make any sense. You can't push an object and have it come backwards towards you just from friction. That doesn't make sense. So friction always matches the force you're pushing with, unless you're pushing with more force than friction can possibly counteract with. So in this case, the force of friction is 6.8 newtons, which is equal to the applied force. So the block doesn't move. Part C, calculate the maximum magnitude of static friction acting on the block if a 2.1 kilogram object is placed on top of it. Okay, so basically this has now changed our mass. So mass now is 3 plus 2.1, which is 5.1 kilograms. The coefficient of static friction is still the same because it's a property of the material of the surface. So just because you have more mass doesn't change what the surface is made of. So therefore the coefficient of friction is still the same. So that's still going to be 0.5. And so the force of friction is mu times the normal force, which is, that's mu s, which is mu s times, remember the normal force is equal to gravity because the block is just horizontally on a table. So this is mu s times mass times g. So 0.5 times 5.1 times 9.8, which equals about 25 newtons. And finally, part D, determine the coefficient of kinetic friction. Okay, so for that, we need to go back to this number that we haven't used yet in the question. It takes 8.8 newtons to keep it moving at a constant velocity. Okay, so that's the maximum frictional force when the block is already moving. So the frictional force equals 8.8 newtons. And we already know the normal force from part A. I think in part D we're assuming this 2.1 kilogram object from part C is not there anymore. Because this 8.8 newtons was based on the original 3 kilogram block, not based on the combination of the two objects. So the normal force is the same as part A, which is 29.4 newtons. So therefore mu K equals force of friction over force of normal. It's the same formula as mu S. It's just now we're talking about the block moving instead of first starting to move. So 8.8 divided by 29.4. 0.3.